As I said when we learned about our trends, electronegativity is our most important one, and that's because it keeps coming up and it has an influence on how our chemicals and molecules actually behave. So, maybe pause, talk to a neighbor. What is electronegativity? And maybe we remember that electronegativity is a measure of how easily an atom attracts electrons. I'm going to say that. Okay, so in the past we've talked about that as a pattern, right? We know that our fluorine is our most electronegative and that there's kind of a spectrum of different electronegativities. Now, to make this extra easy for you, we're actually going to have values for electronegativity. I think it's, right here. So this is in your packets. I recommend you go find it. But you have this available to you now, so you can always just quickly check what something's electronegativity is and actually get numbers for it. And you can see on that chart below us, F has a number of 4. That is the biggest number on the whole chart, right? So the bigger the number, it's saying it's good at attracting electrons. So low electronegativity means they're not really holding on to those electrons, right? Low electronegativity, barely holding on to those electrons, more likely to lose valence electrons, like our metals that end up with positive charge. High electronegativity, more likely to gain electrons, better at having negative charges, and it's also going to change how they behave in covalent stuff. So it's going to help us understand how they behave. Cool. So again, you have this chart available to us, and I'll teach you how to use it. It is in the packets. I recommend you find it there, but here's a version of it too. So you can see the overall pattern. There are some exceptions, but we can just use this going forward. Okay. And then this is going to be important for figuring out what it means to be polar. Okay, so I bet you, we know some things that have poles. We've probably heard of that before, right? Like a magnet has poles. The Earth has poles. And what this term really means when I say polar, I mean it's something with two oppositely charged poles. So something with two sides that are opposites. That's something that's polar. And we're going to have to figure out how that applies to chemistry in a sec. Feel free to pause at any point or slow this down if you need, but or you can always look back at this video if you missed something. The key is also on Canvas, but let's keep going with that. So where this comes in for us is with our covalent bonds. So you guys know a covalent bond is when something happens with our electrons, when we share our electrons, right? But we haven't really talked about this before. Just because they're sharing electrons, it doesn't mean they're sharing perfectly equally. Okay, and I'll be more clear about that in a second. When you are sharing perfectly equally, that is called a non-polar covalent bond. But what if one partner is better at pulling on electrons, better at attracting electrons, better at being electronegative? Then they're not sharing equally, and we call it a polar bond. Right? So the reason sometimes it's unequal is because there's a difference in electronegativity. And we call that being polar. We also sometimes use the word dipole. Dipole just means di is two, and then dipole. It's just another word for having two oppositely charged poles. like in our bonds if they're not sharing equally, or in our molecule if there's like a positive on one side and a negative on the other. So like, here's what I mean by that. Let's consider, I don't know, you can just think about it theoretically if you want, or you can draw this if you want. Let's say I had this bond, right? And we know that when I draw a line, like in my Lewis structure, that's saying that there's these two electrons that are being shared. And so far, maybe we've kind of thought of those electrons being like perfectly in the middle or something. Like they're perfectly shared. But in reality, it's kind of more like this. It's kind of a tug-of-war situation where those two are sharing, but one of them is way more electronegative, right? Fluorine is our most electronegative atom. So yeah, those electrons are there. Yeah, they're sharing. They both get access, but the fluorine is pulling way more. So they're still connected. They're still shared, but those electrons are kind of hanging out way on this fluorine side. They're not in the middle. They're being pulled to one side, and we call that polar. Because remember, electrons are negative, right? So if my negative stuff is on one side, then we end up with one side of our molecule being overall a little bit negative. It's not a full negative. It's not like one loses and one takes, but it's more negative on one side where all my electrons are hanging out. So when we look at our things, the more electronegative element ends up with a partially negative charge. And then the less electronegative thing in the partnership, in the bond, ends up being positive a little bit. Like, it usually has a certain amount of electrons, and now it doesn't, so the lack of negative stuff makes it kind of positive. These are weird little symbols here. Like I said, it's not a full negative. It's what we call a partial negative. So these little symbols are for showing a partial. How about you practice writing them real quick? It's kind of like, I do it like an 8 that I don't finish. Some people make it more like a curvy D, but something like that. So practice that, and then we put the little charge on it. The other way we label, I'm sorry, there's like no space here. You can put this somewhere else, like up on the top of the page if you need. But also I'm going to show, so if I realize I have this weird difference where one thing is a little bit negative, I'm going to label that with these charges. And I'm also going to throw a dipole arrow on that. All that means is that it's an arrow that we draw that points towards higher electronegativity. It points to like where the electrons are going. It points to the negative area. It points to the more electronegative side. I'll show you that in some examples. So first, we're going to focus on bonds. So just a partnership, right? Two things connected. And let's talk about how we tell if that is polar or not. So what we're going to do is look up the electronegativity values for our two partners, for the two atoms in the bond. Okay, and then we're going to compare those. We're going to see if there's a big difference, making it polar, or if there's not that big a difference, making it non-polar. So my two values, we're just going to find the difference between them. We're going to subtract the big number from the small number and see what the difference is. And if that number is bigger than 0.4, greater than 0.4, you can write it out in words if you prefer, we say it's polar. If it's less than or equal to 0.4, then that's nonpolar. So again, nonpolar, they're sharing equally. One isn't winning that tug of war. They're not different enough. While polar, one is pulling way more, and we end up with like an uneven amount of electrons. So let's take a look at these examples. So I'll do two with you, and then I want you to try them. Okay, so what we're going to do, we're going to look up the electronegativity. So again, that's in your packet. It's also on this table. that you have on the previous page. So this question is about H. And I see right there that H has an electronegativity of 2.1. Or sorry, 0.21. And then this H also has an electronegativity of 0.21. Cool. So then we get the difference. The difference is 0, right? So since that difference is smaller than 0.4, we say that this type of bond is non-polar. Okay, so it's based on the difference between those numbers. Let's try this one now. So we're going to look at our previous page or at our packet. We're going to look at the table, and then we're going to find C, and we're going to find O. Here's oxygen, here's carbon. So let's look at our two numbers we have there. I have it was 2.1. Sorry, I'm trying to look at the table on my phone. So, I was right the first time. So 2.1, same thing though, right? 2.1 versus 2.1 is no difference. So that's still nonpolar. And then this one is 2.5, and this one is 3.5. So, what's the difference between their electronegativity? It's 1, right? 3.5 minus 2.5 is 1. And 1 is bigger than 0.4. So this one is called a polar bond. Okay, and it says I want to draw partial charges on my polar bonds. So that means I want to show which side is negative and which side is positive. So when I look at these numbers, the big number means it's more electronegative. It's better at attracting electrons. So this side is where my negative charge is going to be, because that side has all those electrons. And this side is going to be partially positive. And I'll show that arrow too, just pointing towards the more electronegative side, pointing towards where those electrons are going. I just draw it like alongside my bond. Okay, so how about you pause this and try the other examples? Help out your neighbor. Welcome back. Hopefully this has been paused, and now I will go over these. Right, let me try to, sorry. Sorry, I'm trying. Oh, okay. No, I don't want that. Awesome. Okay, I'm not cutting any of this. I am trying to get electronegativity values on my phone. So I don't know, skip forward or something. I'll just be here. Okay. Yeah. So this one, this is 2.5, this is 2.1. That's a difference of 0.4, which we call nonpolar. Carbon is again 2.5 and hydrogen is 2.1. Again, that difference is only 0.4, which we call nonpolar. 2.5, 2.5. Definitely, if there's no difference, we call that nonpolar. And then this one, this was 2.1, this one's 3. A difference of 0.9 is going to be polar. So if anyone had trouble with those, maybe pause again and help out your neighbors in figuring that out, but those are the nonpolar and polar. For my polar bond, I want to label where my electrons are going. My arrow is going to point towards the more electronegative, the bigger number, and that's where all my negative electrons are, and the other side is partially positive. Okay, so if needed, practice that a little bit more. Maybe whoever feels confident can share with the class like how to do these. But if you guys feel okay with that, let's look at this next situation. So this page, again, we learned how to tell if a bond is polar or not. But what about if we have a whole molecule, a Lewis structure with multiple lines, multiple bonds? Is that polar or not? So the way we do this, and this is pretty challenging, like it might take it's kind of a lot to keep track of for a lot of us, so, practice with it. I'll show you a few tools we have to help out, but we just talked about a bond being polar. But that doesn't necessarily mean that our overall molecule is polar. Okay, so the way we're going to do these problems, we're going to have to first look at a bond. So let's look at this bond first, right? We have an oxygen, and there's a bond to the H. So let's look at our electronegativity values for a sec. Let's think about this bond. I have H and O, and I know that this is 2.1, and this is 3.5. So is that a polar bond? I would say yes, absolutely, that's a polar bond. So this is a polar bond where my electrons are being pulled up towards my oxygen. And then there's another bond, another OH on this side, and there's those electrons being pulled up towards my oxygen. And then on this side, we have CO2. And again, the bond I have is O and a C. We already did that one together. Remember? This is on the previous page. This is a polar bond. Oxygen is more electronegative, and it's being pulled towards oxygen. But let's think about this right now. Again, I think that it's helpful to think about this as like a tug-of-war situation, right? Whether or not those electrons are perfectly shared, or if someone gets to like kind of hog the electrons. Notice this shape, right? I have carbon and then straight out linear bonds, right? So this is why the shapes matter, because depending on the actual 3D distribution of electrons, maybe I'm going to be even overall, or maybe I'm going to be uneven. Uneven meaning polar. So, weird thing here, even though it does have polar bonds, since they're both pulling the same amount in both directions, overall they cancel out. So because these cancel out, maybe I'll say that, I'll write it out just in case that's helpful. Geometry, like the shape. Okay. So for honors, I'm going to encourage you guys to try being able to think through this thoroughly, like being able to think through, oh, my arrows are straight apart, or my arrows are not straight apart. They're canceling or they aren't. I think that's like the most thoughtful way of doing this. Let's look at this water again. We said that those are two polar bonds, right? But then you see here, they're not canceling out, right? Like, yeah, this one's coming left, this one's coming right, but they're both kind of going upwards. There's what we would call a net dipole, right? So this one is a polar molecule. And you really have to think about in 3D, right? Like, we know from yesterday that this is a bent shape. That's how you know the bonds are actually going this way and not canceling out. Where if you thought they were linear, like this, you kind of would think they cancel out. So that's pretty challenging. But, those of you who have worked with, like, vectors before or, like, want to challenge yourself, I would encourage you to try thinking about these that way. But for a lot of us, that's kind of challenging. So I want to give some tricks and stuff to kind of help with this whole polar versus non-polar molecule thing. So here's the summary. There's a few different tools here that you can choose to use to help you out. So to be non-polar, if all your bonds are non-polar, sure, like then there's no tug of war at all. Like there's no chance of you being polar. But the tricky part is that even if you do have polar bonds, if you have a symmetrical, symmetrical. It's spelled over here if you can't read my writing. Shape. And then polar molecules, you need polar bonds, and you need those to not cancel out. You need asymmetry. Okay, so like other words you probably know, when we put an A in the front, that means that like it's the opposite, right? So symmetry, it means it's the same on the sides, right? Asymmetry means it's not. So again, this is kind of hard though, because we're thinking about 3D molecules. So like, let's look back up here for a sec. If I just showed you both of these before talking today, you would probably say that they're both symmetrical, because you're used to like kindergarten, like a butterfly, where like that's what symmetry means, right? But we're talking about in 3D, so it has to be like symmetrical in every direction. So like on this one, I bet if I just told you like, is this symmetrical, you would like divide it there and be like, yeah, the two sides match. It is symmetrical. But what if I divided it that way? It's not symmetrical, right? I could rotate this and it would not, like the sides are not actually the same. So that is pretty tricky. Again, here are some tricks for it. Here's this decision tree. If you're having a lot of trouble like being like, is it symmetrical? I can't really tell. Here are the other tricks. If it has either of these, that means it is asymmetrical. Okay. So those are your tricks. I know this is kind of a lot to just throw at you, but it'll take some practice. I want to clarify what the bubbles mean. Lone pairs on the center atom. So that means just in the middle. So same as yesterday, it only really matters what's happening for the middle atom. And if the middle atom has lone pairs, automatically that is not symmetrical, asymmetrical. It might be polar. If it has different terminal atoms, so terminal, like termination, like that means like end. So terminal atoms, that just means like the outside ones. So I don't know, in case this is helpful, like these are the terminal atoms. While this one is the central. Just to clarify the wording used in this visual. Okay, so that's a lot. I'm going to show you 2 examples, and then you can like start working on some stuff on your own. I'm going to do these 2 with you guys. So these are some examples. And this is kind of step-by-step guide. Like first I have to do this, then I have to do this, then I can do this. Okay, so let's start. The first question is, does it have polar bonds or non-polar bonds? So that means I have to go and check these bonds. So my bond is, and you can write this wherever. You don't have to write this, but I just want to show you what I'm doing in my head. My bond is NH. And I wonder if that's polar or not. So like we did on the last page, we have to check our numbers. And this is 3, and this is 2.1. And hopefully you agree with me that that is polar. So yes, it does have polar bonds. Sorry, not the best setup on that, but the bonds are polar. Okay. So maybe it's polar overall. We have to check. And then, is it symmetrical or not symmetrical? So again, this is kind of hard. You can use that simulation from yesterday if you want to see like in 3D. But like looking at it at first, you might think that it matches. But if I flipped this upside down, it would not be the same anymore, right? Like I have these electrons here. And I can use this guide. I have a lone pair on my center atom. And automatically that means it has to be asymmetrical. Okay? So it has polar bonds and they don't cancel and it's asymmetrical. That means it's a polar molecule. Okay? So I know that's a lot of steps, so use your tools as you're practicing. Let's look at this one. This time I have carbon and chlorine. So first I need to know, are they polar or nonpolar bonds? So again, that's based on those numbers. I have 2.5 on this, and my chlorine is 3.0. So those are polar bonds, but then let's look at our shape. This one is symmetrical. There's no dots on my middle atom, and all of my sides are the same. It's perfectly symmetrical. I could rotate this, I could flip it, I could look at every direction, and it's still symmetrical. And that means even though it had polar bonds, if it's symmetrical, that is a non-polar molecule. Sorry, I forgot to, on this one, since it is polar, let's put our charges on there. All my electrons are being pulled towards my nitrogen. So I end up with a kind of negative nitrogen, and all my other stuff is positive. Okay, so I know that's like a lot of tasks, but I'd like you to practice today for the rest of your time. You can apply, so with the rest of your time, I guess I should say, you can do PS 4.3. You can do all of that packet now if you'd like. And we're able to finish the 3D molecule. So we did this yesterday. We did the first 2 pages, first 3 pages, I think. That next part, it's going to ask you to do this. So you'll have to draw the Lewis structures again, and you'll have the 3D shape, but then it will also ask you if it's polar or not. I'm going to say, please use your time to work on these, but maybe don't turn them in yet, because I'm very happy to check your answers on this, because I do care that you do it correctly. So maybe try them today, but then maybe Monday we can check in about them just to make sure you get it before you turn it in. Okay, so again, if you missed any of this, the notes are on Canvas, or you can watch it again on your own. I have suggested videos on Canvas as well, but hopefully this was an okay intro, and you guys can use the rest of your time wisely. Please help each other out. Talking and working together is totally fine. So I will hopefully see you later.